and then this morning with our warm-up problem, we went through basically the proof of the derivative of tangent and cotangent. From here on out, I want you to remember what they are. We could also do the same with secant and cosecant. Secant is the same thing as 1 over cosine of x. Cosecant of x is the same as 1 over sine of x. And if we do the quotient rule with those and simplify, we get to these derivatives. I don't want you to have to worry about that every time. So what I want you to do is write these down, put a big box around them, maybe a star, highlight them, something, but you have to know these. You have to know these. And if I give you a pop quiz, you better know them on Monday, on Tuesday, on Wednesday. Okay, we went through the proofs of tangent and cotangent, and then I'll save you the trouble. The derivative of secant is secant x tangent x, and the derivative of cosecant of x is negative cosecant of x cotangent of x. Do you see some patterns? Do you see some patterns? Nobody sees a pattern. Okay. We'll look at, I'll let you write it down and then look at a pattern. Okay, so do you notice how the tangent and cotangent derivatives have a similar derivative? And how secant and cosecant kind of have that similar pattern? Okay, that's something I want you to take note of.
Any function that starts with a C has a negative derivative.
Any trig function that starts with a C has a negative derivative. The derivative of cosine, cosecant, and cotangent all have negative derivatives. That is an excellent observation that will probably help many of your peers in this class. Okay. Oh, like the secant tangent. Okay. Do you see how these kind of have some relationships happening?
Yes.
Okay. All right. You need to know these. I can't make it any more clear than that. Okay. Let's try a couple derivatives.
What is like the real world use of the derivative of trig? Who's using that ever except for math teachers?
Well, so a lot of this derivative stuff, you're not going to really understand why we do it until we get to the next chapter when we do application of derivatives, and that's really when you're going to see it. Okay? So we're going to talk about minimums and maximums and how to find those with derivatives. Have you ever been in a situation where you're trying to maximize or minimize something? Okay? Engineers are in that situation all the time. Okay? Is that going to be a good enough answer for now?
I guess. Yeah.
Okay. You guess. Yeah, I know. A lot of this right now is we need to know how to take derivatives, so in the next unit we can use them to our benefit to find something. Okay? Okay, write this down. G of x equals x minus tangent of x. I don't know. I think the reader is including it more often than you. All right. So our derivative. Trenton, what's the derivative of x? 1. All right. Pierce, what's the derivative of minus tangent of x?
Less secant squared. Yeah, well, it simplifies.
Like that?
Because tangent is secant.
Mm-hmm.
Oh, it's not.
So what should this be right here? So this should be like that?
Yes.
Yes. You sure?
Yes.
Okay. Derivative of x is 1. The derivative of minus tangent of x would be minus secant squared of x. We good with that?
Yeah.
Write this one down. If I can get it there. My goodness. What rule do we have to use?
Product.
Okay. Product rule, because it is x times secant of x. We have a product. The only way to take a derivative is using the product rule. So the derivative of our first function times the derivative of our second, just our second function, plus our first function times the derivative of our second function. Okay, and I really don't like that it just says 1. So we have secant of x plus x times secant of x tangent of x. Don't get fancy, just leave it like that. Okay, I know there's a secant of x in common, but it does you no good to factor it out. Just leave it. Next chapter we'll factor it out. Okay. All right. I'm going to give you a derivative. I'm going to give you about 2 minutes to work together at your pod to come up with a derivative. Work together. Do what you think is the best route.
I got yeah, but I have to create it. Yeah, because otherwise I leave it over the weekend and then it'd be aggressive.
It'd be just be sine x.
Did Gracie?
Sine squared x.
Okay, how many of you use the quotient rule? Everyone use the quotient rule. Okay, sounds good. Okay, Alex, tell me what you have for your quotient rule.
I said negative sine x times sine x. Minus cosine x times 1 minus cosine x. And then over sine x squared.
Would it be positive sine x because it's a negative cosine?
Yeah, it's negative cosine x, so that would be positive sine.
Okay, so this right here, the derivative of a cosine is negative sine. So what happens when we take a derivative of a negative cosine?
Positive.
Okay, so this is Alex's quotient rule. Is this what you got? Okay. I don't disagree. Nobody did this way. Is this mathematically legal?
Yes.
And what is 1 over sine? And what is cosine over sine? So the derivative of that would be negative cosecant cotangent minus a negative cosecant squared x, which is what that's equivalent to. But we could use trig identities up front to simplify our expression before we take the derivative, and then the derivative is not as complicated. I'm not saying you have to, it's just an option. Yes?
So if we did it the top way, would you want us to just leave that raw? Like and not even try to like not trying to simplify it.
Yeah. Yeah.
Okay.
No, you gotta cook it first.
I loved his word choice of raw.
Yes.
Okay. No? Okay.
I'll just go back.
No, I'll look through it. It's fine. I don't think anybody's in a big hurry today.
Yeah, that's dang sure.
You all look very tired.
We have a nap.
I'm not, dude, I'm just chilling. I got actually tired. Like actually.
Like, Trenton, I hope that you can take a nap on the bus because I'm very worried about you. Okay, like you brought your pillow and everything? No. You'll just have to use like, or it doesn't matter, you don't even need it. Okay. Like, I'm worried about you falling asleep like right now. Okay, all right, so let's talk about notation. Hey, why are we rock, paper, scissors? Not gonna happen. Okay, let's talk about notation. Y prime, F prime of X, dy dx, ddx of f of x. That all means first derivative.
Uh-oh.
Second derivative.
Write these down.
That is up to you.
So we're just doing second.
The second one I'm gonna
I was having a good day.
Well, because I feel like the last one.
Well,
So
it's
we
been-
actually have to do
No, but look.
That would be that's what the y.
Basically, it's the B versus X.
Oh, because over there is just
Okay, so second derivative, you're going to see 2 tick marks. Y double prime, F double prime. Okay, when you have the dy dx notation, you're going to see the squared.
Why is the d squared y and then d is x squared?
So this is basically, because y is like the function that we're taking, so y doesn't ever change. So it's the second differential of y, where x is being derived twice.
Okay.
Okay. Dale, do you have a question?
Now we're going to be doing a lot of derivatives of derivatives.
Mm-hmm. Because we also have a third derivative. Where we have 3 tick marks.
There's more space on that. Is there a fourth?
And then find the
Yes.
derivative.
Yeah.
And then
Like
it's
like that.
well, it's split in half.
So
So
if
it's
you want
like
a linear
4,
one,
5, 6.
Like
you
5.
need to do just layers.
Yeah.
Like
4 and 5.
like 4, 5.
So like the second derivative of a
I'm
given
gonna
function is linear.
Technically for 1 second.
So the third derivative of a given
If I
function would
find
be
the fourth derivative, you can
Okay.
okay.
But what if you have a constant in the beginning?
Then you keep getting 0, 0, 0, 0.
Oh, it's done.
Because the derivative of 0 is 0.
But you wouldn't do that because that'd be
No,
one.
that would be a waste. Okay. Now, is it going to be efficient if I'm taking the 17th derivative? Y prime 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 prime. No. So once you get to the 4th derivative and beyond, then in parentheses, it's not an exponent. It's just instead of saying prime 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 prime, prime, we put that number in parentheses. I warmed up this one. Like vocalists, you know, they warm up. Yeah. Or theater, like theater people. You do like tongue twisters to warm up. Do I have theater people in here?
What?
Are you a theater person?
Absolutely not. Nothing against theater people. It's just me personally. I don't have that talent set.
I think you do.
You should try out for Legally Blonde. I think you get L.
I'll be the dog. I'll be the dog.
Okay. So, I might ask you for the 17th derivative, but there are times where you actually don't have to take the derivative 17 times to know what it is. Okay?
Yes, more hats.
Well, like, Allie, you were talking about the derivative of 0 is 0 and the derivative of 0 is 0. If I ask you for the 17th derivative of x to the 5th, it's going to be 0. Because you're going to be able to take the derivative 5 times before you start getting zeros for your next derivative. Okay? Well, you wouldn't have to. Okay? So, write this down.
I already know that's how it
Write it down. We've got a lot of extra chit chat today. A lot of extra chit chat today. Driving me bonkers.
You're right.
Extra chit chat. All right. So what is our first derivative?
3x to the second minus 10x plus 6.
Done. All right. Our second derivative.
6x. 6x.
6x minus 10. Okay. The third derivative would then be what?
6.
And our fourth derivative, which means our fifth derivative, would be 0. Was it necessary for me to write all of that down? No, because we have a cubic function. By the time we take 3 derivatives, we're getting to a constant, to where our fourth derivative is 0. Our fifth derivative is also 0. Okay? All right. Your homework is going to be broken up to some trig derivatives and some, like, more than the first derivatives. But I also want to talk about this problem right here. What I'd like you to do is, so take 2 minutes and draw this diagram. It's not going to be the first time you're going to see a problem like this, so I want to make sure that you can go back into your notes and look at how you did it. Okay? Draw the diagram, and then write this down, what I have underlined in blue. Raise your hand if you need more time. Okay.
Oh well.
Okay, so I'm asking you for h prime of 0. Can I get your attention, please? I'm asking you for h prime of 0 when h of x is f of x over g of x. So should I plug in 0 right now? No. What do we need first? We need the derivative of h, and then we can plug in 0. Okay? Now, you're wondering, how am I going to take the derivative? I don't know what f and g are. We don't need to. We know that f of x is being divided by g of x. And when we have any function dividing another function, what rule do we use for our derivative? The quotient rule. So all we have to do is use our quotient rule. F prime of x times g of x minus f of x times g prime of x all over g prime of x squared. Not prime, not prime. I got excited. I said prime too many times about 5 minutes ago. Now it's stuck in my head.
But how do you know which one you use?
Which one what?
You use, there's 2 numbers.
Okay, so we're going to get there. Now it's asking us for h prime of 0, right? So h prime of 0 is going to be f prime of 0 times g of 0 minus f of 0 times g prime of 0 all over g of 0 squared. So we're going to use our chart to find each of those values that we can then simplify to one number. Okay, so help me out with the chart. What is f prime at x equals 0? And what about g at 0? Minus f of 0
2.
times g prime of 0. Negative 1, right? All over g of 0 you told me was 5. So we have negative 15 plus 2 all over 25. That wasn't so bad, right? All it was the rule, and then we read the chart to plug in our values. Okay? We have 5 minutes left.
I have a question.
Yes,
So a chart like that, we have to make it?
it will be given to you.
Oh.
And it will tell you, like, so I gave you the chart, and I gave you what the function was. We used a general rule for the derivative, and then read the chart to plug in numbers.
Okay.
Okay? Not here. Yeah, we're done, I think. Yep, we're done.